Hi everyone and welcome to my presentation video in which I will present you our research paper towards the optical character recognition of DSLs. We can find a lot of DSL snippets in images like manuals, student assignments, or in graphical DSLs that are complemented with textual languages. It could be great to extract them in order to have examples for machine learning tasks, do an automatic assessment of these student assignments, improve the recognition of these graphical DSLs that include textual language, or include this parsing into a language ID in order to extract the sentence from the image. But how can we automatically extract these DSL sentences? Using optical character recognition. But what is optical character recognition? Optical character recognition is a technology used to recognize text inside images, such as scanned documents or photos. OCR technology is used to convert virtually any kind of images containing written text into machine-readable text data. Language data includes dictionary of words, grammar rules, etc. Generally, OCR works as follows. First, we preprocess the image, for example, converting to grayscale or applying some filters. Then we detect the lines of text, possible words, and characters. We produce a ranked list of candidate characters based on training dataset. And lastly, we post-process the recognized characters and choose the best character based on confidence from the previous step and the language data. This language data includes dictionary of words, grammar rules, etc. In our work, we are going to see how to apply these OCR techniques to textual DSLs. For our work, the main challenges are error-free recognition, which is essential as any minimal error could result in a syntax error when loading this expression into any language IDE. In DSLs, punctuation signs are applied in a very different way compared to natural language. The current OCR engines try to return the closest word in the dictionary, so the quality of the result decreases when used to recognize DSL expressions, since each DSL has its own concrete syntax. This problem also occurs with domain names as they usually concatenate natural words. We propose different strategies in order to improve the recognition quality. We tested the default model as a baseline. We can see an example of a recognized expression and the problems that might appear. This example is an OCR expression that checks if a property is unique. Firstly, we are going to focus in the arrow operator, as the default English language doesn't know what this operator is and replaces it with the greater than operator. In order to fix this, we propose a WordPress strategy called DB that includes the punctuation signs of the DSL, like operators, into the default model. As we saw, the default model only recognizes punctuation signs that are present in natural language. For this approach, we have to retrain our OCR model once for every DSL that we want to recognize. This approach allows us to fix a very little part of our expression. In the second strategy, which is an extension of the previous one, we are deleting all English words and adding lexical information of the DSL itself, such as keywords, function names, or types. An example of that is the function isUnique used in the expression. As the previous approach, we have to generate our model once for every DSL that we want to recognize. This approach allows us to repair all the words related to the DSL, but how can we fix the other errors? We have our third strategy, which is an extension of the previous ones, and in this approach we include to the model the domain names of the expression in addition to the names in the DSL. As different expressions written in the same DSL, in example OCL, may have different domain name sets, depending on the domain itself. For example, we will add the keyword unique primary identifier with all the other words. This approach has the disadvantage that we have to generate a new OCR model for every expression that we want to identify, but allow us to recognize most of the expression. The last strategy is a very different one regarding the previous ones. Instead of creating a new OCR model, we use a name-based repairing algorithm that we built on top of the default model in order to see if we could improve the base model by only applying a simple repairing algorithm. This algorithm takes the list of possible words that could exist in the recognized expression, being these words the DSL, dictionary of keywords, and function names are the dictionary of the domain names model of the recognized expression. We have an empirical study in which we want to solve the following questions. Which are the most common errors when recognizing DSL snippets? Are there font-dependent errors? Can we load the recognized snippets into an IDE? Which of the strategy improves the baseline model? Which is the performance penalty for the strategy? Many questions have occurred to us in the development of this work, but in this presentation we are going to focus on the last two. In this empirical study, we have parsed a dataset of OCL expressions and loaded them into the use tool to see which of them are valid for our experiment. After that, we generated an image for each font and expression, making a total of 3,250 images. Here we can see all the used fonts and an example image with the Deja Vu mono font. In order to recognize them, we are using the Tesseract OCR engine. We have chosen these fonts in order to have an heterogeneous set including handwriting-like fonts. In this image, we can see an overview of the experiment. As I said before, we are creating images from the OCL dataset as no previous dataset of OCL images was found. Then, we use the Tesseract OCR engine to perform the image recognition for every setup. In the last step, we try to load these images into the use tool and we perform an analysis step. In this graphic, we can see the number of expressions loaded in the use tool for each strategy. This metric is aligned with our error-free recognition challenge. In the results, we can see that almost all approaches improve the baseline model in almost every font, being the reparation algorithm the best case scenario in recognizing expressions by a significant margin. Also, we can see that the recognition performs worse when using the handwriting-like font. Conversely, we can see that the repairing algorithm and the DPLD are the worst case scenario regarding performance, although they are also very similar to the baseline model. This is due to the DPLD model has to generate an OCR model for each expression that contains the domain name for that expression. Also, the repairing algorithm is a post-processing step that we built on top of the OCR reconstruction, so it could imply a performance impact. Fonts 6 and 9 are the worst cases where the algorithm performs the worst, but is mostly due to its implementation. So here we have our roadmap. We want to integrate OCR support in language IDEs. For that, we have to define a systematic process to automatically derive OCR support for any DSL given its specification and domain data. We want better OCR output repairing for DSLs, as there are a plethora of approaches to deal with syntax error and compilation errors that we can use to improve our results. We can also make a graphical DSL recognition, as a proper text recognition will help toward this goal, as well more mature techniques able to identify general shapes from computer sources or could be handwritten drawings. To finish, here we have our conclusions. Different strategies can be applied to improve the recognition quality of OCR engines for DSL expressions. We have an empirical study. We have studied how these strategies help improve the OCR quality and the overhead that they introduce. Our results are that current OCR engines empowered with a repairing strategy have potential to be integrated in language IDEs. We have identified and described a research roadmap, so one aspect that promisingly deserves further study. So that's all for today. Thanks for watching, and I'm looking forward to answer any of your questions.